All right, to finish our discussion on energy released in reactions, we're going to look at a couple of more challenging examples from the diploma exam, mostly from the past. So this question here, it's a really good one. It ties in a lot of concepts in physics 30. It's an absolutely phenomenal question. So we have uranium-238. It undergoes alpha decay to produce a thorium-234 nucleus and an alpha particle. So the decay has been shown here. So the decay of U-238 and thorium-234 and the alpha particle forms an isolated system. So when we have an isolated system, this is telling us that any external forces are not relevant. So F external is 0. This means conservation of energy applies, conservation of momentum applies. Hint, hint. In this system, the energy equivalence of the mass defect is observed as an increase in the system's kinetic energy. So what they're saying is that for E equals delta mc squared, the energy part, the E, is represented by this increase in the system's kinetic energy. So the uranium-238 nucleus is initially at rest and then decays. Both thorium-234 and the alpha particle move away from the location of decay. The thorium-234 nucleus has a mass of 3.89 times 10 to the minus 25 kilos, and the alpha particle has a momentum of 8.4 times 10 to the minus 20 kilogram meters per second, and a kinetic energy of 5.3 times 10 to the minus 13 joules. We would like to find the mass defect of the system and the mass of the uranium-238 nucleus. All right, there's a lot to process here. This is a really challenging question. This is by no means an easy question. So here's what we have going on. So we have uranium-238, and then eventually it's going to decay into thorium and alpha. Now, by conservation of momentum, if this thing wasn't moving to start with, it has no momentum. So what that tells us is that when our two particles move away from one another, the total momentum of this system must be equal to 0 as well. So that means they have to move in opposite directions. So by conservation of momentum, or physics principle number 4, we know the following. We know that the momentum of our uranium nucleus is going to be equal to the momentum of the thorium nucleus plus the momentum of the alpha particle. So for our purposes, let's call right to be positive. Now, we know that we have 0 momentum here, and we are given a lot of information about the alpha particle. We know its momentum, we know its energy. We don't know much about thorium, however. So let's determine the speed or the velocity of the thorium particle. So we have this. Now, I've just said the alpha particle is going right here. It could be going left for all we know. It doesn't really matter. As long as thorium and alpha are going in opposite directions, it doesn't really matter. So the velocity of our thorium particle is going to be the negative of the momentum of our alpha particle divided by the mass of our thorium particle. So we are told the momentum of the alpha particle, it's 8.4 times 10 to the minus 20 kilogram meters per second. And then we're going to divide that by the mass of the thorium particle, which has also been provided. So we have this divided by this. So what we're getting here is we're getting about negative 2.159 times 10 to the 5 meters per second. Now we might say what is the purpose of this? Well, keep in mind, we're talking about the increase in the system's kinetic energy being equivalent to the mass energy equivalence, or the mass defect relates to the increase of the kinetic energy. So to get kinetic energy, we need half mv squared. We're given the kinetic energy of the alpha particle, but we don't know it for thorium. And to do that, we need the speed of the thorium particle as it decays. So we do have that. Now, what we have been told, that energy equals delta mc squared. This is going to be this energy is the increase in EK, or the change in kinetic energy of the system. Now, the increase in kinetic energy of this system, so we're going to have after, kind of like we're looking at EK final minus EK initial. So after this decay has happened, we're going to have the kinetic energy of the thorium and the kinetic energy of the alpha particle. And then initially we're going to have the kinetic energy of the uranium, which we don't need because it's at rest. Now, the kinetic energy of the thorium is going to be half the mass of the thorium times the speed of the thorium squared. So we don't actually need that negative. That negative is just telling us it's traveling opposite to our alpha particle. And then I could write out half mv squared for the kinetic energy of the alpha particle, but in the question we're told the exact value for that kinetic energy. So we're not actually going to bother writing that out. It's already given to us. So we have half the mass of our thorium. We have that 3.89 times 10 to the minus 25 kilos. We have that speed that we calculated. We're not going to worry about the negative since we're dealing with scalar quantities. And then to this, what we'd like to do is we'd like to add that kinetic energy that's given in the question. Now, a lot of people at this point would want to say, in terms of physics principles, they're using conservation of energy here. You're actually not using conservation of energy at this point. Like you haven't said, E kinetic plus E potential at one point equals E kinetic plus E potential at another point. You're just using an equation for kinetic energy. So you have not used conservation of energy. So this is going to give me an increase in kinetic energy of the system of 5.39069 times 10 to the minus 13 joules. Now we're told that that is the energy equivalent to the mass energy equivalence. So we know that this, based on what we've been told, that is going to be equal to delta mc squared. So let's find the mass defect now. So this was kind of the first part, the second part. So the third part now, we know that the mass defect is going to be that increase in kinetic energy divided by c squared. So we have this 5.39069 times 10 to the minus 13 joules. And then we're going to divide that by the speed of light squared. Alright, let's see if my calculator wants to cooperate this time. Right, so we are going to get about 5 point, and for significant digit purposes, at the end of the day, we only actually want 2, but I'm going to write some extra digits here. Times 10 to the minus 30 kilograms. So based on this, my mass defect is going to be about 6.0 times 10 to the minus 30 kilograms. So that mass is what got converted to energy, which we were told is the increase in kinetic energy of the system. So that's the mass defect, which we were asked to calculate. And also I should add, because we use this equation here, E equals mc squared, this is physics principle number 6, because this is the mass energy equivalence. The last thing is we've been asked to find the uranium-238 nucleus's mass. Well, let's look at our definition of mass defect. The mass defect is going to be the mass of the reactants minus the mass of the products. Well, in this case, our reactant is uranium. Our products are going to be thorium and the alpha particle. Now, I just calculated the mass defect. I've been told the thorium mass and the mass of the alpha particle is on the data sheet. So from this, we know that the mass of the uranium particle is going to be the mass defect plus the mass of thorium plus the mass of the alpha particle. These are things that we can deal with. So we have that 5.9897 times 10 to the minus 30 kilos. To that, and I'm really cramming my work in here, sorry about that. And then to that we're going to add that 3.89 times 10 to the minus 25 kilos. And then from the data sheet, the mass of the alpha particle is this 6.65 times 10 to the minus 27 kilo. So let's add all of that together. And again, sorry I had to cram the work in there. So if we do all this, we're going to get about 3.9566 times 10 to the minus 25 kilograms. Or what we're just going to say, for significant digit purposes, we're going to say that the mass of this uranium-238, it's roughly 4.0 times 10 to the minus 25 kilograms. So that's a really challenging question. There's a lot of little steps in it. But that's why when you have large context boxes, it's very crucial to carefully read the question. All right, let's finish up with another diploma example here. So we have the following information. So we have this reaction here, we have this reaction here, and we're told reaction 2. We use it in nuclear reactors in Canada. So if we're told it's used in a nuclear reactor, that's pretty much a guaranteed hint that it's fission. And then we have 1 kilogram of uranium fuel. We're able to produce 6.11 times 10 to the 13 joules of energy being released. So which of the following rows identifies the fission reaction and compares the energy released in 2 reactions per kilogram of fuel? So reaction per kilogram. Now, let's have a look at this. So first of all, the fission reaction is reaction 2 because we have heavy splits into smaller plus the presence of nucleus, or neutron. So this is fission, this is fusion. So reaction 2 is the one we're looking for. So in terms of comparing by kilogram, fusion's always going to win this one. So when we're looking at comparing energy per kilogram, fusion produces more energy per kilogram than fission. So reaction 1 is going to release more energy than reaction 2. So what we're looking for here is C. And now we're told the mass equivalent of the energy released by burning that uranium fuel is A.BC times 10 to the minus D kilograms. Well, this is the using of the E equals delta MC squared, or delta M is equal to E over C squared. Right, so we're told the energy released, it's at 6.11 times 10 to the 13 joules. And then we have that 3 times 10 to the 8 meters per second, all squared. So that is going to give us our mass defect in this case. Divided by this squared. So we're going to get about 6.79 times 10 to the minus 4 kilograms. So in the form A.BC times 10 to the minus D, we have A, B, C, and D. So the 4 blanks we're going to put here are 6, 7, 9, and 4. So that question there, that's meant to be a nice, easy one. Again, get that confidence up near the end of the exam. So last thing, and this is a tricky thing that gets people, it's asked on the diploma quite frequently. It will ask you to compare the energy of fission and fusion reactions, but you have to be very careful. They may ask you to compare energy released per reaction or per kilogram, and this is an important distinction. So fission actually releases more energy per reaction compared to fusion. So if we're looking at just the individual reactions, fission's going to release more energy. If we're doing it on a comparison per kilogram, fusion releases more energy per kilogram compared to fission. So if you're being asked to compare the two, make sure you're looking, is it per kilogram or is it per reaction? That's a really important and very critical distinction.